Hello, welcome to this webinar about maritime ammonia and the technologies on board. My name is Celine and I am a technical advisor in Ocean Highway Cluster. For those of you who are not familiar with the cluster, we are a network for hydrogen and ammonia solutions in the maritime industry. We have previously arranged webinars where we gave an insight in ammonia projects in Norway, as well as bunkering solutions in context to the Enova support program for ammonia vessels. Today, we will get an insight in possible technologies on board the vessel. You can see the agenda on the screen. First out is Wärtsilä. He will talk about their combustion engine. Alma Clean Power will talk about the solid oxide fuel cells, and Amogy will finish up with. And after each presentation, there will be a Q&A session. Please send in questions during the presentations with the Q&A function or in the chat. If some of you want to speak up using your microphone, please just write your name and I will give you the word afterwards. The webinar will be recorded and will be sent out to all registered emails. I think that was all from me, so please, Wärtsilä, you can take the screen.
Very good. Good morning. Is the line working now well?
Yeah.
Very good. I try to let me know when you see.
Yeah, it looks okay. Yeah, it's fine.
Very good. Yeah. So it's a pleasure to be here. So my name is Tuomas Linna and I'm responsible for the ammonia industrialization. So I'm a father of the 25 engine and of course 25 is the first one that goes for ammonia in Wärtsilä. So that is I have the pleasure to be also now here. So just going quickly through this. So I start from the safety as we normally do, and then I tell a little bit about why we have the internal combustion engine for this one, what it can do, then how it can be converted into the existing fleet, and then something about performance, and then let's reserve time for the questions. So I try to be quick, even though I have 9 slides. On the right, you can see the picture of the ammonia test engine, which is similar to the first ones that will be delivered, and on the left side you can see the system that comes with it. So I just put this here. So the safety is of course driving the development, but also the outcome of it. So it needs to be safe to use. And that we secure in the internal collaboration and external collaboration. And I'll get back to that one. But this is very, very important to do well, as we all know. So this holistic approach that we are using, so we want to, we have the whole ammonia system there from the bunkering to the exhaust treatment. And then together with our partners, so with customers and the classification societies, we then want to explore all possible problems that they may be, so that we can tackle those in the design. And if not, if there is still something, then during the operation, we want to ensure that nothing happens. So then we are able to have it's still compared to diesel solution or LNG, it's more expensive, but the capex is relatively okay, and the opex of course. So that is the approach that we have is addressing those both. So here are some good things that why ammonia burns well and why the internal combustion engine is very good. So we know that this is well proven technology, which can be translated relatively easy to burn ammonia and turn that to shaft power. So we have the existing safety concept, and we are using with 25. We are using the LNG type of combustion and the safety concept as well, which is a very, very good foundation to cope with the rules and to co-create with the rule creators. So this is the good starting point. Then the second point, so of course the internal combustion engine has tens of, probably thousands of millions of running hours altogether, but we know the basic technology relatively well. so that is the technology itself is pretty robust. The upgradability is something that is very, very good. So we know that we can convert the existing fleet. So of course, then the business case dictates that which type of engines you want to convert, because you need to do the R&D work there. But that is a good advantage there. The fourth point, the multi-fuel engine. So you have a perfect backup, and this is of course in marine something that we all appreciate, that there is an instant backup right away. The same asset can do that with the backup fuel. The power density is good, so that fits for all kind of vessels. And then we have, of course, different kind of load profiles, and usually the engine is pretty good to take those loads. It's not perfect, but it's pretty okay to go with most of the vessel demands. And then together with the after treatment, so we have been able to demonstrate very, very good performance and very, very close to zero emissions, which is good. Not all is yet industrialized, but the test results are very promising. I get to that in the later part of the presentation. And the shaft line efficiency is on the same level as with the traditional fuels. I don't spend much time with this slide, but I just want to show that we are focusing with the different platforms. So running different type of engine concept on the small scale and the bigger scale to get big enough picture, because usually if you test only with the one, then you get the features of that one. But when you have repetition and the different kind of things like we have at Stord and at Vaasa in small and big scale, then you really learn. And this is, I guarantee that this is the right approach before you go to the field. About technology itself, so there are basically we can divide those into two. So we have either liquid or ammonia or the gaseous format. So you can play with that one. So ammonia is good in that respect, that you can decide that which format you bring that to the cylinder, and both can be then divided into smaller different kind of concepts, and with those different test platforms we have tested very many different kind of things, and from there then we have made the decision. So we have not decided that which we don't ever use, but we have decided which one we go first, and that is the gaseous way, using the type that we are using with the LNG engine. So always having the small micropilot there, which ignites and which can take immediately the backup if needed. So if there is some system, some problem in the ammonia feed or in some safety system, then the operation continues. It just turns that into diesel. Thinking about the upgradability, so there we have done our mapping. So we have the modular structure in our engines, and the newer platform, the better that is. But we have tracked that what are those things that we need to change when we do the engine conversion. And on the left side, on the top, you have from the diesel to LNG, and then from the LNG to ammonia, then after that one. You can do that directly from the diesel to ammonia, that's no problem. That we actually did in the lab engine. So our 6 lab engine, which started the diesel validation of 25 platform. When it had completed its work, then we made an exercise. So we took our service resources who did the conversion from diesel to ammonia in lab. But of course, what we need to say about the conversion on vessels, so if you have an existing asset, then the engine is playing the relatively small role. So of course, ammonia tanks take big room, as we know, and the safety needs to be in the vessel level taken into consideration. So I would say that the engine itself in the engine conversion is a small thing. We are all the time talking about and thinking about the big picture. So if you have such a case, then we are happy to be part of that design. So then we have our fuel gas storage solution, and then ship design guys part of that dialogue. Concerning performance, so we brought the Wärtsilä 25 ammonia solution into market last year November with the 70% greenhouse gas reduction promise. That doesn't mean that is where we end, but that is something that where we started this journey from. And when I talk about the greenhouse gas reductions, it is the greenhouse gas equivalency from tank to wake. So there is a little bit laughing gas which is part of this equation. In practice, we are doing already better with that industrialized version, but this is now the what we can guarantee with that product. With the lab, we have of course done already a couple of years ago the next steps, and we are proceeding with those ones then. So there is on one side actually, or the big picture is to optimize the engine in a new way, and there are different parameters actually to optimize. And thinking about the greenhouse gas potential that the N2O has, so then we know that when you minimize that, you actually then the efficiency becomes the secondary thing. So that is really important to bring close to zero. But there is the N2O, then of course the ammonia slip, NOxes, and then the ammonia share and the efficiency that needs to be optimized. Already without the after treatment, so we are able to get the N2O level low, and the 70% can go easily with that one. But with the after treatment solution and the optimizing it correctly, then we are able to take the next steps there. So this is then all the time thinking about the local and global point of view in the emissions. And then get into this collaboration part that I also started this with, so to ensure that we do it together safe. So we have several customer cases ongoing, which we are soon to close or to contract. So there we are talking about 25 engine and then this whole solution, so having from the bunkering to the exhaust gas mitigation. Then many of you may have the existing engines, 32s, 34s, or the large bore engines, 46, etc. So the conversions are also possible for those ones. The industrialization decision needs to be done though. But what we are doing now with 25, then we can use the same things so technically that is possible for the other engines as well. It is just more about that. What is the business there, and what is the how big market is. So then we make those decisions. But now with the 25 actions, then we are proceeding also and paving the path to the other engines as well. But I don't know how many minutes I use, but I tried to be very, very quick just to cover these main topics that I thought. And I was thinking that we take more the collaboration then if we have time. So
yeah, the time is okay. So
yeah,
if you do have some more, you can add it, but it is okay to stop as well if you're finished.
Yeah, right. I think this is then good time to start the discussion. So any questions to me?
Yeah,
I'm happy to.
Thank you for the presentation. We received questions in the Q&A here related to ammonia slip. So the question is ammonia slip kept close to zero even at partial or low loads, such as in port operation or working in hotel loads?
Yes, it is. So we bring it to very, it's not zero, but it's very close to zero. So it's something which is acceptable to the classes. So we are talking about only some tens of ppms. How we tune the engine is that with all the loads where you are able to use the ammonia, which is now actually the whole. Yeah, we are now from 25% to 100% load. So there you are able to use the ammonia, and then the whole system works with that one.
Next question here. You mentioned that gaseous ammonia inject may be better. This is different than what is used in two-stroke engines where it is always liquid injection, similar to LPG. What are the advantages of gaseous injection in four-stroke? Also, what is your current value of pilot fuel percentage?
Very, very good questions. I don't mean to say that it's better, this low pressure. We selected that one because we think that from the safety point of view, it is the quickest and best way to enter into market. You can also do and we have good results with the high pressure injection. But thinking about the high pressure ammonia there in the engine room and the leakage, then we just concluded that having the low pressure less than 10 bar in the gaseous format is better from the safety point of view to start this journey. But both work well. What was the last part of the question? But sorry that I
no problem. What is your current value of pilot fuel percentage?
Right, we are using now in the industrialized version at the moment a little bit higher, but we will bring it soon down. And the record is something that you hardly see it, so it's very small, so it's way less than 1%. What is then the right level there? It really little bit depends on the load. But in all the cases, we are going with the industrialized versions also above the 70% greenhouse gas reduction. So it means that the ammonia share is higher. So I don't mention exact number there, but it will be very high in the same way as in the DF engine or the traditional LNG engine.
Okay, a new question. How are you preparing for the crew training for maintenance and operation of ammonia engines?
Very good point, and good that thanks for taking this up. This is something that we are working with our Land and Sea Academy, and we are preparing the all kind of training courses. So we of course start from the internal persons who have been developing this. So we develop together with our R&D resources those. But we will have then all the needed trainings for all our systems, and also happy to collaborate also with on the vessel level if there is some demand. So we want to be there, and this is actually mandatory because we need to ensure that the system is safe, but we need to eliminate that somebody misuses it. So that is really something that. Thanks for taking this up. This crew training is something which we need to do together, right?
Yeah, and also the last part of this same topic, how are the crews accepting the increased risk? Have there been any issues regarding that part?
There is lots of discussions that which vessel, and I think that those workboats are the first one to go, and those where there is not so many crew members. Or passengers, but we remember the discussion with the LNG also how similar it was 20 years ago or so, so. But I think that the rule or the guidance that DNV has been using, that we need to have the same safety level as with the LNG. This is something that we need to aim at. And thinking about the ammonia, so of course it's and we need to humble with that one. So that's clear, but it's still technology. It is still something that we just need to do right. There are also very many good aspects in that one. So for example, with the LNG, if you get the leak, you have pretty cold stuff coming out from the tank, which will destroy everything that it hits or will damage. With the ammonia, of course, that's very bad if you have a leakage. The good side is that even the small one you can sense. But this is something that we need to do right, and that is also something that what our company management Håkan Agnevall has also emphasized much, that do it safe. Do it safe together with your partners, because if we are not doing it safe, then we are postponing this. And of course, we are then causing some dangers for people, and that we cannot do simply.
Yeah, I think we have time to just a few more questions. One question is charge air temperature and pressure affecting by running on different percentage of ammonia?
Yeah, we are optimizing it. We so that I don't go into details there, but
No.
but we are taking care of that. But if you have maybe you contact me separately, then I can understand a little bit better. But I don't open this in purpose actually. Also the
No, that's okay.
different conditions. Yeah.
Okay. I think we take the last questions, and maybe you can also answer the questions in the chat and Q&A if you have time during the other presentation. But the last one is, how is the safety aspect related to toxicity of the ammonia taken care of in case of leak or slip that is different from LNG?
Sorry, I didn't hear the. Well, I will take the answer there, and then I will read the question where it is, and then.
Yeah, I have it in my. It was in a personal chat. I can pass it.
Okay, if you put it there, yeah, right, very good.
I can write it in the chat here.
I lost
so then you can...
2 words there, so I want to answer.
Yeah, so the difference between ammonia toxicity and what's the difference from LNG and what's the safety aspects there?
Okay, but I will type there. So thanks for the questions.
Okay, yeah. So thanks for all the questions, and they will be answered in the chat. I think we will go to the next presenter, that is Alma. So Ivar, please take over.
Thank you very much, Celine, and thank you for inviting us to speak at this webinar. And thanks to the cluster also. So, who are Alma? Well, we're a 2-year-old company founded in 21, based on 30 years of R&D from CMR Prototech, a research institute in Bergen. We're based in Bergen with now 35 employees. We see ourselves as a front runner in solid oxide fuel cell system designed to decarbonize the maritime industry. We are today owned by Aker ASA. So what is it that Alma brings to the table? In short, we are developing the most efficient way from fuel to electricity. Electricity is produced in a single step in the fuel cell in an electrochemical reaction with minimal loss. So what you see in the picture here is a 500 kilowatt power system consisting of 6 modules of power modules in range from 80 to 90 kilowatt each. So how efficient is it? Our ambition is to deliver 70% efficiency. That would be included the carbon capture. 60% will, however, in many cases cut emissions by 50% and reduce the fuel costs radically compared to alternative. It also then reduces the need for storage tanks or it added range to your operations on board the ship. So another benefit of solid oxide fuel cells is the fuel flexibility. We have tested the SOFs on the most relevant existing and future fuels with good results. So we see SOFs as a bridge between LNG, the cleanest solution available today and an available fuel, and to the new fuels like ammonia, the topic of today, but also methanol and hydrogen. In the rest of the presentation, I will cover most of what we are doing on ammonia. That has been most of the work till today. So in addition to the efficiency and high fuel flexibility, our solution offers several other advantages. Like other fuel cells, It has no moving part, so the SOFS is silent, low vibration, and has a lower maintenance need. It's a modular design, and that means that the installation can be distributed and optimize the payload. So a ship like, for instance, a car carrier could arrange this in one deck and thereby have more space for more goods and more cars on board. And SOFC is also ideal for carbon capture, since you never mix fuel and air. You have a lower exhaust volume and then high CO2 concentration. So, of course, all these benefits, it basically sounds too good to be true. And of course, there's some drawbacks with this technology. It's still immature, and with that comes cost that is today a bit higher than engines. But that being said, in the lifetime of a power system, the fuel is by far the biggest cost. So, and especially with the future fuels like ammonia or e-methanol, the fuel cost will be quite high for the coming years. So then efficiency kicks in as really important. And you can see in the illustration here that even though the SOFS is twice as expensive as an engine, it's profitable within 2 years for the ship owner. So that was a bit about the benefits or about the technology. And now I'm going to tell you how we are planning to scale this from the lab where we are today and on board the ships. So the first thing we did was last year, we tested one stack module in our labs here in Bergen. That is a 6 kilowatt stack module. And important with that, and we run that on pure ammonia. The important part there is that we could show that the efficiency from 61 to 69% depending on the range. So a really important test to show that this is possible to run ammonia in SOFS. The last year we have been building a 100 kilowatt system, what you see in the picture here, that has been built in our office here in Bergen and at Aker Stord. And here you can see what's inside the hot box where you have one module. This system is still quite a large test setup, so it's quite large, but you can see that the stack module itself is not that large. All of this is being tested at the energy house at Stord. So we had a test readiness review of the 100 kilowatt ammonia module on Stord yesterday, and we hope to be starting it this week. Our test setup is in the our test setup is in this garage, and then Wärtsilä is doing has their engine in this one, and over here you have Amogy's testing. So all the speakers today are doing testing in this building. Next year we will launch our products, and with that the specification, so the size and weight and output, input, all of those things that ship owners are quite curious about. Before we have the first project where we go on board the ship. This is in a cruise ship, so as you probably understand, ammonia is not the first, or cruise ships are not the first applications for ammonia. So we will so this demonstration on board MSC cruise ship will be on LNG, a 500 kilowatt installation that will be kind of in the machine room. And as part of the whole system there. And from 2026 and out, we plan to deliver on several things, both on ammonia, methanol, but also LNG with carbon capture systems. Our plan for industrialization is that today we build things at Aker Solutions. We plan on putting up a pilot assembly line as soon as possible before we have aim at full scale production in 27 at 400 megawatts yearly capacity, and after that global expansion. So the topic today is ammonia, so I would like to just highlight the benefits of SOFs for ammonia applications. Of course, the efficiency we have already talked about. What's unique with SOFs is that when you run it at 800 degrees, you can crack the ammonia internally in the stacks. So there's no need for pre-reforming or anything. So this is very interesting, and what we are aiming to demonstrate now at Stord the coming weeks. There's no need for pilot fuels either. It's pure ammonia that are going into the system. And there's negligible NOx. The numbers here we don't have before we have tested it. When we test in the lab, it's not possible to measure anything because the amounts are so small. But we have reason to believe that it will be low because the rest fuel that is not being converted in a fuel cell are burnt in the afterburner with below the formation temperature of NOx. So and of course it's lower risk with ammonia slip with these fuel cells than in other technologies. As mentioned, we hope that we are on the verge of a breakthrough with this system that you see here. You see the cap module then at Stord ready to push the button in the next few days. Here you can see the setup, the container. You can also see the partners in this project: Wärtsilä, Equinor, Yara, Eidesvik, and supported by Innovation Norway, Siva, and Sustainable Energy. So you see the hot box module to the left with the stack models inside, and you have the BOP system to the right. So what we're going to do on ammonia after we have done these tests, the next ammonia project is a project called Ship FC, where we are going to retrofit 2 megawatts of SOFs on board Viking Energy, a vessel owned and operated by Eidesvik for Equinor. And that is going to be done in 26. So the partners in this project is Equinor, Eidesvik, Wärtsilä Power Solutions, and Wärtsilä Gas Solutions, and on. Yeah. So that was what I had presented. I probably talked too fast as usual, but if you have any questions, I'm here.
Yeah, thank you. No problem. We have a lot of questions in the chat, so I think we're just gonna jump into it. Can you say more about maintenance and replacement of SOFs versus combustion engines? And is the maintenance cost for SOFs significantly lower due to the lack of moving parts?
Take the last part first. That is what we guess. Of course, there's a lot of things you have to replace in an engines. I'm not an expert on this, but we have several people from engine manufacturers in our team here that have been working for Bergen and engines and other. Of course, there's with SOFs, what you have to replace are the stacks, and the stacks are being degraded. So right now our philosophy is that we change everything within the 5 years. So when you have the maintenance interval where you dock the ship, we replace everything. But the systems are being built as modules so that you can use of a simple forklift and just replace one module if needed. But we designed this to last for 5 years, and then we replaced it at docking.
Yeah, and next question is, at what ranges between 0 and 100% load do you achieve the highest efficiency? If you know.
This is a really good question, and that's one of the parts where softs differentiate from an engine, because an engine is, from what I understood at least, most efficient when it run on max load. However, softs, it is more efficient if you offload it a bit. So it's between the 50 and 60%. It is running on it has the highest efficiency. And this is quite useful in many cases, because you often need to overpower to run all systems. So then you can dimension the system so that you are running at max efficiency at where you need to be. Yeah.
It also a question about lifetime, but I guess you answer that one when you're talking about replacing the stacks. But how did you solve the problem of nitronization of metals? If you, I'm not an expert.
Yeah, of
myself.
course. Let me see how we can. Of course, that's one of the night riding is one of the most difficult things with it. And of course, with ammonia, when you combine it with heat, it's of course a nightmare. So to be safe, I think we need to use quite expensive metals now in the beginning, and then we have some solutions to this that I don't want to go into. Yeah, but it's manageable. Yeah.
Yeah. Another question here is comparing fuel cell to ICE. Is there any limitation on the fuel cells in regards to operations and load taking? And is the start and stop time as fast as on internal combustion engine?
I don't know too much about the start time of engines, unfortunately, but one of the softs takes some time to get it heated. So when you start it for the first time, you need 24 hours to get it hot. If it's in idle mode, it can ramp up quite much faster in a few hours. But you need to heat it the first time. So if it's been cold, it takes some time. I guess that's more than yeah. So that's one of the things with keeping in mind with softs is that it prefers to be running continuously, and that is why we aim at the deep sea segments as where we see the most potential for this. We don't see high-speed ferries or any nearshore applications as relevant. It's deep sea vessels where you can have it running continuously, and also auxiliary applications are also where we begin, of course.
I think we have time for one more question, and the question is, what is the estimated cost in euro per kilowatts of the containerized solution that you are showing in the illustration? If you do have any numbers you can share, of course.
No, I think it's please just contact us and you'll get the numbers. Yeah.
That's okay. So we do have some more questions in the chat, so maybe if you can answer them just directly in the chat and the Q&A, if that's okay.
Of course.
So thank you, Ivar.
Thank you, Celine.
Then we move over to the last presenter here today, Trym and Amogy. Ja, det ser bra ut.
Good morning, everyone. My name is Trym Sjøberg. I'm a commercial project manager at Amogy. Started here in the start of May, so a bit new, but learning quickly. Okay, before that, I came from 6 years in the Norwegian Maritime Authority. So to start off, I just want to present our vision, mission. It's to build technology that unlocks ammonia's potential as a clean energy source. And well, some people still call us a startup, but we've grown quite a bit. We're now over 180 employees, and was founded by 4 MIT PhDs in 2020. And just a quick slide about our investors, not to brag, but about how much money we've raised, but we've raised quite a lot, $220 million. But just to show also what type of companies have invested in us, quite big names and important names such as Amazon, MOL, AP Ventures, which includes Equinor and Nysnø, Mitsubishi Heavy Industries, and so a lot of big names in the maritime industry have put interest in us. And these are our locations worldwide, headquarters in Brooklyn, but also facilities in Houston. And our European headquarters based in Stavanger, that's where I sit. And we're testing installed. And we have someone in Oslo and a commercial team in Singapore as well. This is just a quick view of our team in a European team, 9 people from different backgrounds in the maritime industry. So quite a good team. So yeah, why is ammonia such an interesting future fuel? Well, one of the main things is the ammonia infrastructure today is quite advanced because it's the second most produced chemical in the world. Over 200 ports, 4,000 kilometers of pipelines in the US for moving ammonia. And yeah, this is something that we feel is very important, something that can be built upon. And also, since it's been used for over 100 years, the safety aspects from ammonia are quite robust on land. So that's something as well that we feel is important that we can build off of. And yeah, the interest in ammonia has also been growing quite a lot, with over 15 ammonia bunkering projects announced, among other things, Yara in Norway. And also shipyards have accumulated lots of orders for very large ammonia carriers in the last years. So the fleet is growing. And also on a governmental level, for example, Norway, through the NOVA program, has its own ammonia fueled vessel program, offering up to 80% soft funding for additional capex costs when using ammonia solution compared to a traditional solution for both new builds and retrofit. And big companies such as Equinor as well have had an offshore vessel tender for a vessel with dual fuel ammonia. So, I mean, the interest is there. That's what I'm trying to just put out there. So it's an exciting time for ammonia. So that was that. But now to our technology, which I guess is the most interesting part. We do ammonia cracking, and we're one of the most efficient ammonia crackers on the market. Have a high energy density, and we do the cracking on relatively low temperatures, and with 0 carbon emissions is what our technology gives. Here's a simplified overview of our technology. So we start with ammonia storage, and then we feed gaseous ammonia into our reactors, where it reacts with our catalysts and heat and we get the product of nitrogen and hydrogen. And since there's some ammonia left in the reformate, we also put it through our adsorber, which removes the ammonia, and then the remaining product is delivered to the hydrogen fuel cell, PEM fuel cell, and you get electricity. So that's pretty much what our product does. So you kind of get the advantages of storing ammonia and the advantages of using hydrogen. And we have demonstrated our technology quite a lot, not just theoretically, but also out in the field. And it started with the ammonia-powered drone in 2021, a 5 kilowatt system with a small miniature version of our system now, and it was able to fly approximately 3 hours, which was and had a weight of 22 kilos, which was quite interesting. Here you can see a small video, and then from there we went quickly on to our ammonia-powered tractor. It was a 100 kilowatt system. It was a John Deere tractor. Took out the original propulsion system and everything, and put in our system. And yeah, it was the farmer said also it was a very interesting system because he was dreaming about using the ammonia from his farm to power his tractor. And from there, in under a year, we also had our ammonia-powered semi-truck, a 300 kilowatt system, which didn't drive on roads, but I went around a track at highway speeds for quite a while. And also, compared to the other ones, you can see this was the first time we fit the technology in a good form factor to show that that we could also do that. So there's been a rapid scale up in our technology towards commercial readiness, and the most interesting demonstration is upcoming, and that's our tugboat, which will is planned for late summer, which will be the world's first carbon-free ammonia-powered tugboat vessel. And we have quite a lot of partners and have had a large focus on safety, even though it's not a commercial vessel. But we've had talks with DNV, US Coast Guard, and Lloyd's Register, and being supplied green ammonia from Yara. The naval architects are Seed Job, and electrical systems and integration is with Seam. So it's been quite a large undertaking getting all this to work. It's been a bit harder and took a bit longer than we expected, but it's been a very important learning for us, and we've kind of see it as a good thing that we know kind of the issues that our customers will eventually face as well, so we can handle those when they come. But yeah, it's a interesting and important learning for our company. So, as well as these demonstrations, which are important milestones towards commercialization, we also, which is almost as important or as important, testing our power pack at the energy house that Alma talked about at Stord. Looked around the world, and that seemed it's pretty much the best place to do it. So we're testing our 200 kilowatt pack there now. And also, we're building our facilities in Houston. So that will planned opened in 2024, and that will be a testing and manufacturing facility. So our product as of now is mainly our Amogy Power Pack, our 200 kilowatt solution, which is made of our, as you can see, a reactor, our adsorber, and a fuel cell. We don't make the fuel cell, but right now we're mostly partnering with Ballard and PowerCell. But in theory, we could use other fuel cells as well. So here's a mock-up of how it can be put together, or these systems could also be placed in different places. But yeah, this is a more tidy presentation. And then also we have our containerized pack, 400 kilowatt solution. So it's two of the other systems you saw crammed into into a 20-foot container, which is great for rebuilds, but also could be useful for new builds which need versatility to their systems. And we have some interesting pilot projects that we're working on now. At Maritime, we have our Hanwha project, which you can see we have in this image here, 3 of our containerized solutions on the back of the vessel, which is very interesting, working with one of the largest shipbuilders in the world. And also, just to show our versatility, we also have the project with Terox for power generation on construction sites as well, because there's a large need for green energy with all the upcoming regulations for what you're allowed to emit in construction sites. So with all the new battery-powered construction vehicles, they need a solution, and that's what we're trying to create. So our main technology is the cracking. So in theory, we could work with many different things. Right now, it's PEM fuel cells, because that's the most mature technology here. But in theory, we could also in the future work with Alma and their solid oxide fuel cells, or maybe hydrogen engines, which some people are working on, and turbines. So our power pack is what it is now, but in the future, yeah, we'll see what the future holds. So we're also, I mean, there's options for versatile configurations of our technology. For example, you could have only our system together with batteries, or, for example, in combination with something like Wärtsilä's ammonia engine to increase your efficiency. Depending on your operation profile and load profile of the vessel, you could optimize this. So yeah, it's important to remember that our system can be added in new builds, retrofits to reduce the emission in various different ways. So yeah, that's a short presentation. So I guess our roadmap for on our way to broad adoption in the future. And yeah, that's it. Thank you.
Yeah, thank you, Trym. We just hop into the questions in the chat. The first one is, what is the ammonia cracking capability that can be achieved in kilograms of hydrogen per hour of your largest cracker units?
Sorry, that's I'm not exactly sure of the exact numbers there, but I could probably if send me an email, I could probably get that answered. Yeah.
Yeah.
I'll try as best as I can to answer the questions, but like I mentioned, I've been here since May, so I'm not the most in-depth knowledgeable, but I'll try as good as I can. Or if not, yeah, I'll get a hold of someone that can at our company, of course.
Yeah. I also have some questions regarding what fuel cell technology you use, but I think you answered it at the end of the presentation.
Yeah.
You currently have PAM, but you are open for others as well, right?
Yes, correct.
What is the targeted cost euro per kilowatts for your cracker?
Again, that we don't exactly talk about the cost in the open, but again, take contact and we'll probably be able to share some good figures.
The next question here, could you repeat what you said about the product that is specialized for power to construction sites? What was this a collaboration with another firm? What capacity does this module have?
So what we're planning there is one of our containers, 400 kilowatts containers, which will then together with an ammonia tank and an auxiliary tank for necessary safety equipment and so on, we'll be able to charge battery packs that are at the construction site. So what did I answer the question, or was there something else?
The follow-up question was it this collaboration with another firm?
Yes, it's in collaboration with a company called Terox, which among other things rebuilds construction site vehicles into battery power and rents out equipment. So it's a good fit for
Let me see the next question. In the presentation of the versatile application, you show that 70% of efficiency could turn into 90 or 100. Would 70% be the overall cracking efficiency of your unit?
No, I think I should have mentioned that was just in regard to the greenhouse gas emissions. If, for example, if you're using one of their engines and which has some together with our system, which has no greenhouse gas emissions, and then if you use them effectively together, you can probably get a much better total effective emission than efficient. But that was not compared to the efficiency of the whole system. That's not what it was.
Another question is, you mentioned Houston to be your first production site, but will you also have a manufacturer production site in Europe in like a longer timeline?
I know they're looking into different production partners and stuff now, but I don't think anything is that I know of that's fixed yet. So I guess it could be Europe, it could be somewhere else. That's see what the future holds. Currently, we're not in mass production, so
No, it's still on early phase, of course. Another one for the cracking reactor unit. Do you have a preference for base metal or PGM based cracking catalyst in your power pack? Of course, this might be more technical that you have insight in, but if you do have the answers.
The cracker is ruthenium based, is what I know. But other than that, I'm not that in depth on that area.
I think we can have the last question here. The hydrogen-nitrogen separation system is very energy intensive. And how do you achieve an efficiency of more than 80%?
I don't know
if you want to show a slide, you can.
The 80% was compared to the system itself. It's not 80%. It's compared to other comparable technologies. So that's where that number comes from. I think what we say is like the whole system as a whole, including the fuel cell and reactor, is around 40. Yeah. So that's where the 80% comes from.
Yeah, I think the clock is 11, so I just want to thank you, Trym, and all of the other presenters here today. I will, I can collect the questions, and maybe if the presenters want to answer them, I can include it in the email, where I also will send out the recording when that is available. I will also add the link to previous webinars after the request, and that will be sent out during the next days. So thank you again to the presenters, and thank you to all for joining us here today.
Thank you for having me.
Bye.
Thank you. Bye-bye.